Welcome to the third lecture on effective stress. In the previous class, we have discussed about the effective stress concept for saturated soils and partially saturated soils, and we have also discussed about effect of the fluctuations of water table on the effective stress. Then we also introduced another definition of pore water pressure, that is neutral stress. In this lecture, we will be understanding the situation which is above the water table. As you all know, depending upon the climatic condition and size of a particular soil or pore spaces of a particular soil, the soil which is above the water table can remain also in saturation or in partially saturation. That means that a coarse grained soil can be partially saturated above the water table, or for a fine grained soil, even if it is certain meters above the water table, it can remain a completely saturated condition. So, this particular behavior is called capillarity. So, this we will be discussing in this lecture. So, this is an effective stress 3. So, in the previous class, as you all know that we have discussed about effective stress concept and for saturated soils and partially saturated soils, and effect of fluctuations of water table on effective stress and consequent effects we have discussed, and neutral stress or neutral pressure or pore water pressure difference we have understood, and why the effective stress is called effective and why it is very important in geotechnical engineering also discussed. So, as you all know, we have also beginning of this effective stress concept, we have defined the groundwater table. So, let us look the definition of groundwater table once again. Groundwater table or phreatic surface is the level to which the underground water will rise in an observation well, pit or other open excavation into the earth. So, here the groundwater table or a phreatic surface it is also called, is the level to which the underground water will rise in an observation well or pit or other open excavation into the earth. So, in addition to every soil in the field is completely saturated up to some height above the water table. That is what we are discussing, that every soil is saturated up to some height above the water table. So, what are the reasons behind this particular behavior that we are going to discuss in this class? So, this particular behavior is attributed to a phenomenon called capillarity of soils. So, this particular behavior of soils remaining saturated even above the water table is called or attributed to capillarity of soils. So, capillarity arises from a fluid property known as surface tension, which is a phenomenon that occurs at the interface between different materials. So, capillarity is a phenomenon which occurs between the interface between different materials. Look, like in case of soils, this is what we have is the water, air and mineral grains. The inner walls of the mineral grain surfaces will act as some boundaries for the water to rise above the groundwater table. So long as the water or rising water remaining in contact with the groundwater table, then it tries to rise above the groundwater table. So, this depends upon the climatic conditions and the gradation or a particle sizes of or pore spaces of the soil mass. So, for soils, surface of water, mineral grains and air, these are the three different materials which are required to be considered. So, as you all know, the definition of surface tension caused by each portion of the liquid surface exerting tension due to the molecular attraction, because it has got an attraction towards the other material which is adjacent to it, and adjacent portions of surface are objects that are in contact with the liquid surface. So, this is something like a property of fluid which is interacting with different materials. So, in the case of soil, it is the mineral grains and air and water. So, the phenomenon in which water rises above the groundwater table against the pull of gravity, but is in contact with the water table as its source is referred as capillary rise. So, the phenomenon in which the water rises above the groundwater table, but it is in contact with the groundwater table which as its source is known as capillary rise. The rate of capillary rise is also defined as capillary conductivity. The rate at which this capillarity rise occurs is called capillary conductivity. So, water is sucked up into the pores of the soil mass in this zone on account of the surface tension of water, and which is a manifestation which is referred as a capillary phenomenon. So, because of this molecular attraction between materials like inner walls of a grains and water and air interface, this water is drawn into the columns of water which are there above the groundwater table. So, water is sucked up into the pores of the soil mass. These columns of water, nothing but when they get filled with these pores, when they get filled with water, they become something like columns of water. So, water is sucked up into pores of soil in this zone on account of the surface tension of water, and this manifestation is referred as capillary phenomenon. So, this capillary phenomenon has got many practical examples, like around the behavior of the soil in and around the beach, where the soil which is slightly away from the portion where the wave breaks is ready to offer you resistance for walking or motorcycle riding, or away from that zone again is very difficult to walk or very difficult to ride a motorcycle, or within that zone where the wave breaks, it is difficult to even to walk on or stand on that particular zone. So, this particular behavior is attributed to the capillary phenomenon that we will be discussing at the end of this lecture. So, here different cases like water in soils. So, generally what happens is that for a given terrain, the rainfall which has got a surface runoff and percolation, that is whatever the rainfall occurs, that is one is part of the water is percolated and part undergoes a surface runoff. So, this zone above the groundwater table is called Wadow's zone or Wadow's water. The water in the zone above the groundwater table is also called Wadow's water. So, here this particular surface is also indicated as a water table or phreatic surface, where the pressure is atmospheric pressure is 0. So, here is a free water surface. So, this is a typical schematic representation of a river or lake, and here in this zone there is a transient and percolation and capillary water. So, this capillary water which is occurring because of the phenomena which we discussed just now is because of the surface tension, which is a property of the fluid which is actually sucking the water and drawing the water into the pore spaces of the soil above the groundwater table, with the groundwater table as its source. So, this particular water table, particularly this saturation of a Wadow's zone, it also depends upon like climatic conditions. For example, this particular water which is remains saturated because of this particular phenomenon can undergo some drying in case of some arid climates because of the temperature. So, in that case the water which is stored in the pores of soil can get evaporated. So, more or less and it is a climatic, it is a function of the climatic conditions. So, let us look into the capillary water system. In this slide, different zones are shown here, and we will try to define these zones and we will try to understand. So, here the topmost zone is contact water. So, when you come to the bottom, this is the groundwater table where the free surface or phreatic surface exists. Above that, when it is very close to the groundwater table, there will be a certain zone which remains 100% saturated, that is called capillary saturation. Above that is a partial capillary saturation, and above that is the contact water, which is arising because of the percolation of the water because of rainfall or so. So, in the process, this water which is stored in the contact zone is called contact moisture. The water which is stored in the pores of soil because of this percolation which occurs is called contact moisture. So, here in this partial capillary saturation and capillary saturation, which is attributed to the phenomena again like surface tension. So, here if you divide the water zone in the soil mass with groundwater table can be divided now, the saturated zone below groundwater table and capillary zone above groundwater table. So, this capillary zone is again divided into capillary zone with complete saturation and partially saturation zone. So, capillary zone may be divided into 3 different zones with some arbitrary boundaries. These boundaries are very arbitrary, it varies with time and climate. So, zone of capillary saturation, that is where the complete saturation is said to be prevail even above the groundwater table, and zone of partial capillary saturation and zone of contact water. Okay. So, this capillary zone we have divided into three zones, three different zones. One is that zone of capillary saturation and zone of capillary partial saturation and zone of contact water. What is now let us look into the details, like zone of capillary saturation, which is the closest to the groundwater table, which remains in contact with water and which has got this columns of water which is occupied in the pore spaces of the soil, which is resulted in saturation of the soil mass even above the groundwater table. So, above the zone of saturation is the zone of capillary saturation and above is the zone of partial capillary saturation. In this zone, water is connected through smaller pores, and but more of the larger pores are filled with air. So, when the more of the larger pores are filled with air, then that tends to be a partially partial capillary saturation. So, zone of contact water, that is the third zone which we have classified, is the zone of contact water. The water in this zone surrounds the points of contact between the soil particles and also surrounds soil particles, but it is disconnected through pores. So, the water in this zone surrounds the points of contact between soil particles and also surrounds the soil particles, but it is something like this contact moisture is something like a films of water will be surrounded and it is kept within the pore space of the water. So, either due to some flooding or due to evaporation, this contact moisture can be lost. So, here this particular diagram shows for example, a trench excavated here with a retaining structure. So, if you can see here, this particular water level is saturated with phreatic water, where 100% saturation prevails here, and here is saturated with the capillary water. Even when it is remain in contact with groundwater table, it has got the 100% capillary saturation, even 100% saturation resulting due to capillary phenomena even above the groundwater table. So, partially saturated with capillary water, that is this particular one is called a partially saturated with capillary water. Then above that is the percolating water, or whatever we are discussing, which is nothing but contact water, So, here we can see that partially saturated with percolating water zone, that is contact water zone, whatever we have discussed, and this is partially saturated capillary zone, and this is completely saturated capillary zone, and this is our conventional saturated zone with which is below the groundwater table. So, these are the different conditions, like water table conditions which can be possible in this particular subject, where when the rainfall occurs, then we have discussed that percolation will occur and then contact water table is kept, which is very above within the Vadose zone. So, there are for example, if this particular portion of sandy soil is receiving certain water under pressure because of some source of water, either because of some river or lake. So, that can be said that it is under artesian conditions. So, if a well is driven into this particular strata, and the well it is called artesian well, and here that means that this particular portion of the soil will be having additional pressure than that conventional water table pressure. That means that it has got an extra source of water which exerts that additional pressure. Here in the subartesian well, where there is a certain amount of pressure, but not more than this artesian conditions. This is the conventional ordinary well with which actually appears with the groundwater table. So, what we have seen in this slide, the ordinary well, subartesian well and artesian well. So, many times when we are constructing structures on a soil stratus under artesian conditions or excavations which are carried out under artesian conditions, one has to ensure the stability. If the stability is not ensured, then effective stress tends to become 0, then there is a chance of failure or caving in or collapse. So, there are also some situations like the localized pockets of water table which can be possible when there is a lenses of clay. So, that type of water tables are called, those type of water tables are called perched water table. So, that is what it is shown here, a perched water table condition. This is the normal water table. So, but this could be the localized condition where the water is under perched water conditions. So, it is called perched water table. Okay. So, previous slides we have defined and we have introduced capillary rise phenomena. Now, let us look into the theory behind this capillary rise phenomena and let us look how this can affect the effective stress. So, here the definition, a rise in a liquid above the level of 0 pressure, that is at the free water surface the groundwater table is a 0 pressure due to a net upward force produced by the attraction of the water molecules to a solid surface, that is glass and soil. This particular capillary soil capillary phenomena in soils can be demonstrated by immersing a glass tube of open ends in the vessel of water. If that is done, what will happen is that the water will rise into the glass tube. The rise of this water, which depends upon the diameter of the glass tube and cleanliness of the inner surface of the glass tube, that is the cleanliness of the inner surface of the glass tube. So, here the surface tension phenomena with molecular attraction occurs between 3 interfaces where 3 different materials, that is air, water and glass surface here. So, the rise of water, which is a function of particularly the diameter, that is nothing but the diameter of a tube. So, in real cases this diameter of the tube is nothing but the pore size or pore spaces, the size of the pore spaces within the soil. So, a rise in a liquid above the level of 0 pressure due to a net upward force produced by the attraction of the water molecules to a solid surface, that is example here glass and soil. For those cases where the addition of the liquid to the solid is greater than the cohesion of the liquid to itself. So, here this can be demonstrated by immersing a glass tube of small diameter into a vessel containing water. So, we will consider this and then we will try to derive the theory behind this capillary rise. So, here it is shown here. So, this is the AA is the level in this slide, AA is the level at which the groundwater table that exists, that is the free surface where the pressure is 0, and here this is that path taken by the capillary rise. So, this is HC is the height with which it could rise depending upon the pore space and cleanliness or the cleanliness of the mineral grains, inner surface of the mineral grains or the grain wall cleanliness. So, if you look into this, this particular behavior can be simulated by something analogous to a capillary tube phenomena, where immersing a open end tube in a vessel of water can simulate this particular condition. So, let us look into this here, how this works. So, this is a groundwater table, that is the free water surface, that which is nothing but the level AA, and this is the diameter of the tube, which is nothing but which represents the pore space size, that pore size, the D may be the pore size, then this is the rise. So, HC is nothing but the rise which is obtained here. So, this is the D size which is referred here, that is the pore space, and here now you can see the menisci form at the top surface. So, here menisci will be formed at this top surface. So, it has got something like an upward pull and then it is resisted by the self-weight of the water column which is within the glass tube. So, similarly here also the same phenomena, water is pulled against gravity above the groundwater table and which is resisted by the self-weight of the water which is within that column. So, it is reasonable to assume that pore spaces between soil particles of various diameters behave in much same manner as that of capillary shape. So, it is reasonable, it is to estimate that pore spaces between soil particles of various diameters behave are very close to the analogous behavior as that of some capillary tube immersed in a vessel of water. So, vessel of water where that particular surface represents the free surface which is nothing but a groundwater table surface. So, in soils, shapes of void spaces between solid particles are unlike those in capillary tubes. Yeah, it is definitely the pore spaces or void spaces which are not as regularized as capillary tubes. However, the voids are of irregular and varying shapes and size and interconnected in all directions, that is also there. So, the voids of irregular and varying shapes and connected in all directions. So, hence accurate predictions of the height of capillary soil is next to impossible. However, the features of the capillary rise in tubes are applicable to soils as they facilitate an understanding of the factors of the capillarity. So, as long as they provide an understanding of the process of the capillarity, then this can be simulated for predicting the accurate for understanding or facilitate the understanding of the capillarity behavior. So, here in this slide the soil microscopic view is shown here. So, here what has been discussed is that the soil can have interconnected pores of different spaces. So, it can have these pore spaces or pore channels can be in any direction and can be in any shape. So, very difficult to, we have discussed that very difficult to simulate that, but to understand the behavior this to a great extent this capillary tube behavior which is very closely represents the this particular behavior which occurs in this nature. So, here because if you can see here, this is a tube and then this menisci is formed because of the attraction. So, the tube containing water exhibits the positive capillary rise where water adheres to the side of the tube causing the fluid to rise slightly. Suppose if this case if you substitute with mercury, then the behavior is slightly different. Instead of rising, it exhibits something like sinking. The water in the capillary tube sinks down. So, the tube containing water exhibits the positive capillary rise where the water adheres to the sides of the tube causing the fluid to rise slightly. So, this is the microscopic view of the soil shown. So, this zone above which the saturation is maintained is called capillary fringe. So, in this now let us look into how this capillary pressure acts on the walls of the pore spaces or along the periphery of the glass tube under consideration. So, that is the free water surface. So, this is water which rose because of the depending upon the diameter of the tube. So, that is the force with which it could pull the water column water in that water which is occupied in the tube against the gravity. Now, these are the surface tension forces acting all around the periphery of the tube. D is the diameter of the tube which is nothing but the pore size in soil. So, now if you look into it, the F, that is with which it could draw the water into the this diameter of the tube in glass tube of diameter D is nothing but T naught, which is the surface tension, which is the property of the fluid. For water, it is surface tension is 0.00075 kilonewton per meter. So, T naught into pi d cos alpha, where alpha is the contact angle, that is this is the alpha which is contact angle here. For a clean tube or for a mineral grains with clean surfaces, this contact angle alpha is equal to 0. Now, capillary pressure is nothing but force divided by area, which is pi d T naught cos alpha divided by pi d square by 4, that is the area of the tube under consideration. Now, on further simplification, this can be written as UC is equal to 4 T naught cos alpha by d. UC is equal to 4 T naught cos alpha by d. Now, if you see UC is directly proportional to 1 by d. The smaller is the diameter, the greater is the capillary pressure. So, that is required to be understood and kept in mind. Now, what has been told is that for chemically clean glass tubes, alpha is equal to 0. That means that the UC will become 4 T naught by d. So, UC is nothing but the particularly capillary pressure is nothing but 4 T naught by d, where d is directly proportional to the surface tension of the fluid under consideration and inversely proportional to the diameter of the tube, or in real terms the pore size of a given soil. So, soil water exists in small spaces in soil as a film around the particles, and the small pores can act as capillaries So, a capillary is a very thin tube in which a liquid can move against the force of gravity. That is what we have discussed, and water is attached to the glass tube by adhesion. So, a thin film flows up the side of the tube while the cohesion drags more water along. Is something like an extended flexible membrane, it pulls the water against the gravity. So, the liquid rises to the point where the gravity balances the adhesive and the cohesive forces. The narrower the tube, the higher is the water column can rise. The narrower the tube, the higher the water column can rise. That means that the smaller is the pore space, then the smaller is the size of the pore space under consideration, the greater is the height it can raise. That means that if you have got a clay soil, we can expect that the clay soils can have very large heights of capillary saturation than say sandy soils. Or a coarse grained soils can remain only can be subjected to capillary saturation only up to certain height, whereas fine grained soils can be subjected to saturation up to the greater heights even above the water table. So, let us look into the this particular derivation which can be obtained to calculate the capillary rise height Hc. So, again the water table in the vessel is considered. Hc is the height to which the water column rose into the tube under consideration. D is the diameter of the tube. So, F is the force with which it has pulled, and W is the weight of the self weight of the water in the column of the column which is that is in the tube of diameter D. Now, if you take the vertical equilibrium, sigma Fv is equal to F minus W. So, the capillary rise is calculated at which F is equal to W, that is the vertical force with which that is the force with which it is pulled is balanced by the self weight of the water column. So, to that height it will rise and then it will stop at that particular portion, that is the Hc which we are going to obtain from this direction. So, that is what sigma Fv is equal to 0 yields F is equal to W condition. So, now if you write now T naught into Fd, that is for a chemically clean glass tube, alpha is equal to 0, then alpha cos alpha is equal to 1. So, T naught pi d is equal to pi d square by 4 Hc gamma W. This is the self weight of the water in the tube, in the capillary tube. Now, at equilibrium Hc is at a maximum, therefore, the solving for Hc max yields something like Hc max is equal to 4T by d gamma W. Gamma W is the unit weight of water. So, this can be expressed as something like Hc max is equal to 0.306 divided by d, where d is the diameter of the tube, or in reality d can be pore size. So, 0.306 which is actually constant, which is obtained by considering the property surface tension value of a water, which is nothing but T is equal to 0.00075 kilonewton per meter, and substituting in this equation and simplifying. So, D in centimeters, we can yield Hc max as 0.306 divided by D. So, as we said, the narrower the tube, the larger is the capillary rise. Let us look into it, what will happen. For example, as we have got different ranges of particles, so different ranges of pore spaces can be possible. Coarse grained soils will have very large spaces, large pore spaces, that indicates that the capillary rise in coarse grained soil is supposed to be low, whereas fine grained soils have got very small pore spaces, because the spaces are very small. So, it is expected that the capillary rise in fine grained soils is very high. So, let us look into this. So, here again the vessel which is having different tubes of diameter, different diameters, where this D1, D2, D3, D4, D4 is greater than D3, D3 is greater than D2, D2 is greater than D1. So, let us look into it, how the capillary rise can be understood from the previous deduction. So, here Hc1, which is the capillary rise in the tube 1, where D1 is the diameter, which is the smallest which is considered. In this case, the Hc2 which is the rise which is obtained for diameter D2, where D2 is larger than D1. and Hc1 is greater than Hc2. That is one thing which is required to be kept in mind. Here, which is nothing but Hc3, where Hc2 is greater than Hc3 or Hc1 greater than Hc2, and D3 is greater than D1 and D2. In case finally a D4, a diameter of the tube D4, which is larger than all other tubes which are considered. So, the height capillary raise is around Hc4. So, for soils, this pore space is approximated as 20% of the effective particle size. So, effective particle size we have discussed and introduced earlier is D10 is the effective particle size. That means that 90% of the particles are larger than this particle, only 10% of the particles are finer. So, D10 is the effective particle size. So, 1/5 of the D10 particle size is referred as a pore space. Suppose a D10 of say a coarse grained soil is say 1 mm, then the pore size is around 0.2 mm or so. For example, a D10 of a fine grained soil is say 2 micron. So, 1/5 of the 2 micron is a very small pore space for a fine grained soil. So, this deliberation can tell us the smaller the pore space, the larger is the capillary raise. That is what we have understood. The smaller is the diameter of the tube, the greater is the capillary raise. That is what we have understood and we have proved from the discussion whatever we had so far. So, here that is what the pore size D is shown. So, this depends upon the type of the soil. The D can be very small for fine grained soils, D can be very large for coarse grained soils. That means that sandy or a gravelly soils. So, capillarity and soil water energy, the surface tension, the greater attraction of water molecules for each other than the air above at a liquid air interfaces primarily due to that cohesion. So, adhesion and surface tension together cause the phenomenon called capillarity. So, that is what we have discussed. Adhesion and surface tension together cause this phenomenon which can actually draw the water against the gravity and can be kept within the pore spaces. So, the movement of water up a wick made of hydrophilic solid materials, that means that it is nothing but the movement of the water nothing but a wick made of hydrophilic materials. So, capillary movement takes place in any direction. It can be vertical or it can be in any direction in which actually this particular phenomena is occurring. The height of the capillary rise in a tube is directly proportional to the liquid surface tension, addition to the solid surface, that is very much important, and but inversely proportional to the tube radius or diameter and the density of the liquid. So, inversely proportional to the density of the liquid, because in the derivation we have discussed the density which is in the denominator. So, inversely proportional to the density and to the diameter. So, this particular discussion we can also extend to see whether we can generate any correlation or approximate estimation based on the particle size, effective particle size and void ratio of a given soil. So, as we have derived, Hc is equal to 4T cos alpha divided by gamma WD. That is what we are discussing in the previous slide. The capillary rise is inversely proportional to the unit weight of water or the density of liquid. D is the tube diameter or pore size, and alpha is the contact angle. For a chemically clean surface, alpha is equal to 0, T is the surface tension. So, here it is be given as an approximation for soils. If you put T is equal to 0.00074 kilonewton per meter, gamma W is equal to 9.81 kilonewton per meter cube, alpha is equal to 0, and assuming or approximating that D is equal to ED10, that is D is equal to ED10, where D is the pore space and D10 is the particle size. So, E is the void ratio of a given soil, where D10 is the effective particle size. Then Hc is given by an approximation something like 30 by ED10. So, this 30 is nothing but a constant. So, this can be reduced to something like Hc is equal to C by ED10, where C is a constant. So, the estimate may be improved to allow for the effect of grading and grain shape characteristics such as irregularity and flakiness. So, Hc is equal to C by ED10. So, this can be further discussed here. So, rough approximation of maximum height Hc to which the water can raise because of the capillarity phenomenon can be said as Hc is equal to C by ED10, where C is a constant which has got units in centimeter square or meter square, which has got for in case of centimeter square, C is equal to 0.1 to 0.5 centimeter square, and which is a function of grain shape and surface impurities, and E is the void ratio. So, capillary action holds the soil water in small pores against the force of gravity. The smaller the pores, the greater the movement can be. That means that because with this we can say that the pore spaces in fine grained soils very very small, though the void ratio is high for fine grained soils, the pore spaces are very very small. Because of this virtue of this small pore spaces and this particular phenomenon, property of the surface tension and addition of the water, it exhibits this particular capillary phenomenon, and it because of this particular phenomenon it can draw water, and it can keep water within these pore spaces to keep the soil even above the water table under complete saturation. So, when you consider different soils, let us look how when they are having different effective particle sizes and how far they can rise above the groundwater table and remain saturated. Say coarse gravel with a particular typical coarse gravel which is having a D10 say 0.82 mm can have a capillary head, that is HC, of about 6 centimeter only. So, fine gravel 0.3 mm can have a 20 centimeter capillary head. Silty gravel at 0.06 mm can have a capillary head of around 68 centimeter. Medium sand can have 120 centimeter. Silt can have 180 centimeter, that is around 1.8 meters, and clay which is having D10 is less than 2 microns, this can have something like capillary height runs around meters. But because of evaporation and all, many times it is not possible that it remains, cannot be guaranteed that it remains completely saturated, but the chances like it can theoretically it can remain saturated up to certain meters. But because of evaporation, what will happen is that this fringes which are developed, which are remain in contact with water, can be lost, and the continuity is lost, and then it can be subjected to some it can remain in partially saturated condition. But otherwise it can remain completely saturated even above the groundwater table, running into something like 10 meters or so. So, approximate relationship between capillary raise and soil type, if you look into it. So, this capillary raise is plotted on the log scale on the y axis, and effective size D10 is plotted on the log scale on the x axis. So, if you see here, this is the capillary raise HC. So, clay has got here, if you see here, around 10,000 mm, that is around 10 meters here, silt and then sand, gravel, so which is followed. So, this particular property is also considered like wherever we wanted to prevent or arrest this, provide some capillary arrest which is required. When you do not want this capillary action to prevail, then we use this gravel or a sandy soil materials as capillary cutoff materials. So, they can act as a capillary cutoff layers to inhibit the soil exhibiting this this is particularly adopted for man-made structures, where a capillary cutoff is provided to see that the water is not remain saturated, because remaining saturated then there can be changes in the properties of the soil. So, if you plot this relationship between height of the capillary raise in 24 hours, let us consider in a 24 hours how fast it can raise, and the log of the grain size in say in millimeter. So, if you look into it, this curve as is plotted 0.201, 0.01, 0.1 and 1 and then 10. So, HC is greatest for fine grained soils, but the rate of raise is very slow because of their low permeability. So, HC is for example here this theoretically this HC has to be very high for fine grained soils, but here within 24 hours it could not exhibit very high raise because of the low permeability of the soil, which we will be discussing in the next subsequent lectures. So, whereas for certain soils like silt grade and very fine particles, the raise is very very high. So, you can see that maximum for the silt size and very fine sand particles, it is very high. So, how far this particular phenomenon can affect the effective stress? So, that we have to understood now. So, coarse grained soils are only partially saturated even at elevation close to the water level, whereas fine grained soils may be saturated for a considerable distance above it. So, if there is a coarse grained soil or a sandy layer above the clay layer, it can be said that the sandy layer can remain in partially saturated condition. Suppose a clay layer and a groundwater table exists, and then above, if the clay layer continues even above the groundwater table, then it can be said that it can be under saturation because of this capillarity phenomenon. So, here in this case, a particular diagram where this groundwater table is shown, and this is that zone at which that partial this complete saturation is prevailed because of the capillarity phenomenon, and this is the zone, say sandy soil, where the dry soil. So, the pore water pressure can have this particular distribution, because here the water which rose above the water table, above the zero pressure or atmospheric pressure, is can be called as negative pressure. So, here the water column which is drawn and kept within the pore space above the against the gravity above the water table is said to be in tension, and then here the water which is there below in hydrostatic conditions where no flow is occurring can be said that it is under compression. So, it is what you see is that the water above the water table is under tension, that is called capillary tension, and below is positive pore water pressure. So, above this, the distribution of the pore water pressure can be, if there is a partially saturated soil, then it can have a certain reduced pressure, but otherwise this if it is immediately say a dry soil is coming where the capillary raise is almost negligible, in that case it can run like this, a negative pressure. That means that this ordinate is nothing but Hc is nothing but the head, negative head, which is kept above the water table, that is minus gamma WHc, which is nothing but the negative pore water pressure or negative water pressure. That will be there, and then immediately the water can be dropped, the pressure can be dropped to something like zero pressure. So, this negative pore water pressure also referred as something called suction pressure. So, U or UW is also minus gamma WHc, which is nothing but also referred as a suction pressure. So, by substituting the value of Hc, we can also obtain this suction pressure. So, let us see the capillary rise in soil and then stress profile. So, this particular case, we have got a vessel of water, that is represents the free water surface or a groundwater table, and this is the diameter of the tube D, and Hc is the capillary rise depending upon the tube diameter, and this is the meniscus which is formed, which is not shown here, but is a meniscus. So, here UC is that capillary pressure we have calculated F divided by area of the tube, where F is nothing but T naught into pi d cos alpha, which is acting over a periphery of the entire tube of the inner diameter of the tube. Now, this is gamma WHc, that is hydrostatic pressure, that is water column which is there here exhibits zero pressure here and gamma WHc here. So, the net pressure, that is the difference of the pressure which is indicated in red line to the blue line, that is here that pressure is referred to as the pore water pressure distribution. So, that we will get here as something like this, where minus gamma WHc, something like negative pore water pressure here and 0 at the free surface, and then below it continues to be again positive. So, here if you look into this diagram, it looks something like a part of the water above the groundwater table is under tension and the below is under compression. So, capillary rise in soil and how the stress distribution which is affected, let us look into it. So, this is the discontinuous water which can be in the partially saturated zone, and capillary fringe and capillary saturation. So, this capillary fringe to some extent also can exist in the partially saturated zone, and discontinuous water either because of some contact water or contact zone, it can be remained also partially saturated. So, capillary saturation which is in contact with the water table can be said that it can have a complete saturation. Now, what we discussed is that Hc minus Hc gamma W is the water pressure, that is negative pore water pressure or a suction pressure. Hc is that capillary rise above the groundwater table, and here this is that again below the water table, again positive hydrostatic pressure. So, the degree of saturation in this zone can be subjected to variation, it cannot be too easy to estimate, but to some extent this can be estimated by considering the value of the some correlations are there with the degree of the saturation. If you multiply, then we can get the suction pressure to some extent in that particular zone, that is SR by 100 into gamma WHC can to some extent can give the degree of saturation in the partially saturated zone. So, effective stress, how this can be varied with respect to capillarity. So, that we can see. So, in the zone of the capillarity, what we are seeing is that the pore water pressure is negative, that is under tension. So, when you say that total stress is equal to effective stress plus pore water pressure. So, effective stress is equal to total stress minus pore water pressure, that is U. So, this U is now U is equal to minus UC. In that case, now the effective stress is something like sigma dash is equal to sigma plus UC. So, there is an enhancement in the effective stress because of this particular phenomenon. So, this sometimes can act as also giving good support to the soil under consideration. So, here sigma T is the total stress distribution with depth, and here is the gamma WHC. So, here is actually explained here. In this case, when it is undergoing partial saturation is gradually reducing to dry condition here, then this can be said that minus gamma WHC which is not clearly shown here, but minus gamma WHC and then reduced to 0 here, and gamma W this may be the H, then gamma WH. So, if you substitute here, then we will be able to get that net distribution is like this. This shift in increase is because minus HC gamma W which actually gets added to this effective stress. So, it is nothing but to the total stress. So, sigma dash is equal to sigma plus gamma W HC at this particular point. So, it exhibits high effective stress at this particular zone, and then here this particular variation is resulting due to this particular distribution. So, one has to be kept in mind this capillary saturation, this is not generally kept in design, because in the case of say any flooding or any evaporation, particularly case like when this is evaporated, this effective stress can be lost. So, as is because subjected to climatic conditions, so very difficult to consider and kept this in the design. Now, let us look this particular phenomenon with respect to the practical examples. We all know when a lump of dry unconsolidated grains are piled, then it can form a something like a cone of heap. So, the angle of inclination of the cone of heap, the maximum slope which can take is called angle of repose. So, dry unconsolidated grains will form a pile with a slope angle determined by angle of repose. So, the angle of repose is the steepest angle at which a pile of unconsolidated grains remains stable and is controlled by the frictional contact between the grains. So, in general, for dry materials the angle of repose increases with increasing grain size, but usually lies between 30 to 37 degrees. So, around 30 to 37 degrees it takes something like a cone shape, then moment it reaches that particular angle, then the soil starts fail. So, that is the maximum slope at which that particles can stand, maybe around 30 to 37 degrees, and it can increase with increase in diameter, but however it remains in 30 to 37 degrees. So, in the case of dry condition is like this, but the same soil, particularly what we are now considering is that we are having say sandy soil, and then we will see this roll of water with clay soils, it is entirely different. So, here in the same soil under wet condition can be is entirely different. So, let us see, this is that dry condition, what we are saying is that angle of repose. So, this is that slope which is called angle of repose, what we are saying is it can increase with the diameter of the particle, and this angle, suppose if you look at the microscopic view, then the grain to grain frictional contact will be there, with that it exhibits this particular type of structure. So, what we can see is that as you are pouring sand, after reaching this angle of repose, then soil starts slipping. So, that means that is the safe slope at which the grains can stand. But if the same soil is made wet and then it can even remain vertical, the angle of repose can increase very, very high. So, think about building a sand castle in the beach. If the sand is totally dry, it is impossible to build a pile of sand with a steep face like a castle wall. That is how we discussed. It is very difficult to build a steep slope with a dry unconsolidated grain. In the sand is, if the sand is somewhat wet, however, one can build a vertical wall. So, if the sand is wet, then one can build a vertical wall. So, if the sand is too wet, then it flows like a fluid and cannot remain in position as a wall. So, if the sand is too wet, then it flows like a fluid and cannot remain. So, if it is too wet, then it tries to flow like a fluid, and if it is wet, then what can happen is that one can even build a vertical wall. We can even get very high angle of repose conditions. So, that is what has been demonstrated here. If you take a wet soil, wet sandy soil, you can make any shape by putting in a glass and then removing that. So, that is actually is shown here. Then what happens is that here what you are seeing is this is something like a thin film of water surrounding these particles. So, when the water is just sufficient to bind the particles, the film is formed and then tries to hold the particles, but the same water or the some films can be lost if the extra flooding. So, that can actually arise with the flooding of water. That means, if you wet the soil, sandy soil completely, then these films are lost, and then what will happen is that soil starts flowing again. So, slightly wet unconsolidated materials exhibit a very high angle of repose because of the surface tension between the water and the solid grains tends to hold the grains in place. So, a slightly wet unconsolidated materials exhibit a very high angle of repose because of the surface tension between the water and the solid grains tend to hold the grains in place. Similarly, the role of water for when the material becomes saturated with water, the angle of repose is reduced to very small values. That means that here if you see, the angle of repose is reduced and the water occupies the space between these grains and the grain contact is lost. So, the frictional angles have reduced to very low values. So, the material tends to flow like a liquid. So, this is because the water gets between the grains and eliminates the grain to grain frictional contact. When this happens, it starts flowing. Contrary to this, the behavior is entirely different. When you supply for a clay soil or a soil which is having a spectate and montmorillonite mineral, when the water is supplied, it tries to keep in it and tries to swell or expand. So, that particular behavior is shown in this slide, where this is an unexpanded clay and this is expanded clay with pore water molecules. So, soil containing smectates or montmorillonites expand when they become wet as water enters the crystal structure and increases the volume of the material. So, when such clays dry out, the loss of water causes the volume to decrease and clays to shrink and compact. So, this process is referred as hydrocompaction. This process is referred as hydrocompaction. So, when such clays dry out, the loss of water causes the volume to decrease and clays to shrink or compact. So, this particular behavior is called hydrocompaction. So, a different role of water with sand and clay we have seen. And the physical examples of capillary phenomenon we can give something like along the beach, as we said, very close to the beach where it can have very good strength. Away from the beach, the absence of capillary pressure, very difficult to walk or very difficult to ride. In this zone, one can ride the motorcycle or one can chase, because it provides the native columns of water. That is, these pink lines are nothing but the capillary columns are filled with water under tension. So, the effective stress is minus gamma WHC plus say total stress. It becomes something like it has got an effective stress which is nothing but gamma WHC, which can actually have a positive pore water pressure, positive effective stress here. So, that actually can make and can provide a good support. Whereas, when the wave breaks here, so almost it is lost here. So, it is very difficult to stand even in this zone. Away from the zone, again it is difficult to walk because it is getting away from this capillary zone. So, confining pressure results from the column of water hanging on the different menisci on the surface of the beach. That is because of this capillarity phenomenon. And RD of this, if you consider relative density, is more or less same in throughout the area, but even then this particular behavior it exhibits. So, in this class what we try to understand is that a concept of capillarity phenomenon and its consequent effect on the effects on the this effective stress. Particularly, what will happen when you have got different soils, then why the soils tends to remain saturated, and we understood that it depends upon the size of the pore of the soil, the smaller is the pore size, then larger is the capillary height. Then we also discussed that the theory behind this particular phenomenon and why the reasons are attributed to something like a surface tension, which is a fluid property, and then an attraction between the grain surfaces, inner surfaces, and air water surfaces. So, this phenomenon is something like capillarity phenomenon we have introduced, and we also discussed about the theory behind that capillary rise, the rate of capillary rise for different types of soils we have discussed. Then we said that because of the virtue of the low permeability, it can exhibit the very gradual, but it can rise even up to large meters depending, because the pore space is very small. So, in this, with this we will try to we have seen effective stress with in hydrostatic conditions. In the next class, when water is subjected to some steady seepage conditions, how these effective stresses can change and all we will discuss.